a todos, gracias por venir tan temprano. Bueno, para nosotros es temprano, yo les explicaba que estaba todo vacío porque acá se empieza tarde. Bueno, first I want to thank you for coming here. You were the idea to come here to give lectures, and thank you very much for your
Our pleasure.
Sí, vinieron, se propusieron ellos para venir a visitarnos y a querer conocer nuestro instituto, así que es un honor. Y ahora vamos a empezar con Shi-Zhang Qiao, que de la Universidad de Adelaida, que nos va a hablar sobre materiales para energía. Bueno, es el que fundó el Centro de Materiales para Energía y Catálisis, y además es el director del Centro para Reciclado de Baterías de la Universidad de Adelaida. Bueno, tiene una experiencia y una cantidad de publicaciones que impresiona y varios premios, entre ellos y varias fellows, entre ellos el fellow de la Royal Society, y es editor en jefe de Catálisis, y bueno, es uno de los científicos más citados en el área según Inquimae. Bueno, please, Professor Shi-Zhang. It's very difficult for me for pronunciation, and welcome, and thank you very much for coming.
Thank you, Sarah. So thank you, Maria. Also, I'm Shi-Zhang Qiao from the University of Adelaide. So Adelaide is the third university established in Australia. So it's 151 years old. So yeah, so my university, merged with another university from next year, beginning of next year. So currently, my university students is 22,000. After merge is over 50,000. Yeah. So today I would like to introduce my research work on the material as a practice for energy storage and conversion. So 20 years ago, actually, I also work on the mesocore, but now so I focus on the catalyst, organic catalyst for the battery and hydrogen production study. So today, I would like to talk three research topics. One is electrical catalyst for energy conversion. I will focus on the water and seawater steam for green hydrogen production. Okay, the second product is the catalyst for energy storage. I will focus on the metal sulfur battery. The third one is aqueous zinc iron battery. So yeah, I will give a reason why we study that. So for the seawater and the water electrolytes, so we use two the device system. First one they call the proton exchange membrane (PEM) system. The second one is alkaline water electrolyzer, we call the AWE system. So yes, for seawater and water steam, I will introduce two devices. So before I give the talk, I will answer the question why we use seawater for water steam. So yeah, you can see we produce 1 kilo hydrogen, we need 25 to 35 kilowatt and 50 kilowatt electricity. Okay, actually this number is huge, right? So in Australia, impossible for us, they use fresh water to produce hydrogen because we don't have enough fresh water. So so you can see this red zone, the face ocean. So we have enough seawater, right? The second, this reason, so electricity can come from the wind or solar, the energy. So it's easy to produce electricity. So this reason, this the area, this zone is potential for us to use seawater to produce hydrogen. Okay, so for seawater produce hydrogen, we have two methods. One is indirector. Another method is a director, seawater, the electrolyzer. Okay, here, what it means, the indirector. It means we can use the seawater, take RO process, we can get fresh water. Right? This is the indirector. However, for RO water, the quality is not good enough for PEM system. You can see there are a lot of elements inside. So it means that if we use RO water directly, so activity lose the catalyst lose activity very quickly. So we must take a deionization process, get the pure water. Yeah, the first process is very cheap. However, this one is very expensive. So in our research, we must consider, use RO water directly for hydrogen production. Yeah, I will tell you the cross different. Okay, another method is director seawater. This means we can use seawater directly. Yeah, we don't need to treat it. You can see here, we can use the PEM or AWE system for hydrogen production. I will give a detail later. Okay, so first I would like to introduce the PEM system for seawater splitting directly. Okay, for seawater splitting process, we have two problems. One problem is chlorine and chloride produced on the anode. Okay, because the seawater, there the chlorine, right? The second problem is calcium and magnesium hydroxide acetate produced on the cathode side. So it means it's a solid particle cover on the catalyst. Less catalyst lose activity very quickly. Okay, in my research, we combine, chromic oxide and copper oxide together. Okay, chromic oxide is a very strong Lewis acid. It can, attract OH minus produced during, the water splitting. Yeah, during water splitting we produce OH minus. That's why, the absorb on the, the Lewis acid surface. Okay, so yeah, in that case you can see, we can, make the surface of catalyst is the local environment is alkaline. It means the pH value is very high. It's 14. So I'll give the reason later. In that case, we can prevent, set reaction on anode side and the cathode side. Okay, so here, yeah, you can see from this figure slide, you can see normally we can use the copper oxide as a catalyst for water splitting, but you can see here activity not so high. We must add a lot of alkaline inside, increase activity. For both of cases, you can see stability is not so good, right? So you only run the, several hours only. Okay, for all cases, you can see we combine two, metal oxide together. So this all the performance. Keep in mind, we never add any alkaline solution, but this performance is very similar to this one, right? The reason is we just mentioned on the catalyst surface, a lot of OH minus made the local environment like alkaline. Okay, here, first we need to study the OER reaction, the oxygen evolution reaction on the anode side. Yeah, for the particle results is the dashed line. This one is all the catalysts. You can see performance is much better. This activity. So why? Yeah, we use here you can see, so we can use modify rotating ring disc, measure the pH value on the surface. That surface means only several molecular distance. Yeah, we measure the pH value in the surface. So you can see, yeah, if we use 6% chromium oxide and the copper oxide, you can see pH value is 14. Okay, so this one is XPS results. XPS, yeah, we analyze cells 2+ peak. Yeah, you can see if we use copper oxide only, yeah, we find 2 significant peak, right? This indicates chlorine chloride produced. However, for all the case, this one, we never found that peak, right? This indicates, in our case, we never found, the chlorine chloride produced. Okay, one reason. So you can see this one is OH minus concentration on the surface, several molecular distance. Yeah, for all the catalysts, you can see this concentration is very high. It means on the surface, a lot of OH minus, OH minus. They can reject Cl minus from seawater, reject each other, right? So chlorine cannot go into the surface. So this reason, in our case, we never found chlorine chloride produced. However, if we use copper oxide only, you can see this concentration is low. It means Cl minus can go into the surface. Okay. We also study another reaction, is HER, hydrogen evolution reaction on cathode side. Again, you can see compare published results, all catalysts much better. Again, we measure the pH value on the surface in at some the potential you can see here, pH value is 14. Okay, after reaction we can take electrodes out and we use XRD analyze the two material. Yeah, if we use copper oxide only, you can see our peak, right? This peak indicate some metal oxide produced. However, in our case, yeah, very clean, only copper oxide. Yeah, so what reason? So we measure the pH value on black solution, not surface. You can see, yeah, if we use copper oxide only, if we increase current density, this concentration increase significantly. It's about this dash line. This dash line is a precipitation line. Yeah, so this reason for the copper oxide produce a lot of precipitation. However, for our case, even the concentration in the black solution increase, but much lower than dash line. So in our case, we never found any product, any is a solid produced on the surface. Okay, we use a device. To demonstrate, all the material performance. Yeah, this green line. This green line is commercial. This commercial catalyst is very expensive, right? The noble, the metal use pure water. Okay, this use pure water. Yeah, this red square, the line is alkates, is seawater. We use alkates. Okay, this performance is green line already, right? We also study stability. So 100 hours, no problem. Yeah, for another people only ran several hours only. Okay, so I just introduced a PAM system for water splitting directly. So here we use the alkaline, the seawater electrolyzer system. Okay, so normally for the pure water we use nickel catalyst. However, nickel cannot operate in the seawater, lose activity rapidly. Okay, here we use nickel ion, the catalyst. Even that, is unstable, so we must modify by different ion. Okay, so we establish a relationship between the RDH, this material, the OER activity and the corrosion resistance with the ion basicity. Yeah, after that we found that which one is the best is phosphorus is best. Okay, here the detail. We use 7 different ions. Yeah, we establish a relationship between the activity and this corrosion resistance. Yeah, with ion basicity. So we found that this phosphorus, yeah, is the best modification, ion. Okay, first we study in laboratory scale system. Here's a 2-watt system. You can see current density is quite high. It's quite high. Normally, other people only use 100 or 200 mA. This one is 1,000 mA. So we can run 1,000 hours. You can see, compared with the public results, you can see our work is here. The current density is highest. We can run 1,000 hours. We also study performance in industry scale system. So you can see this 1 kilowatt, this is big already, right? Is this system. You can see this state consists of 17, the cell. So this area is quite large, right? Yeah, we can run 100 hours at a high current density. Okay, so this, the AWE system. Okay, so yeah, we also calculate, the price of hydrogen here, very close to, $2 US for 1 kilogram hydrogen. Okay, so we just mentioned, that we cannot use RO water directly. You can see here, if we use RO water for PEM system, you can see here the voltage increasing significantly. So we cannot use RO water. We must use DI water. Okay. However, if we compare the price, if we use RO water, it's very cheap, right? But if we use DI water, it's very, very expensive. So we must consider develop a new catalyst system. New system can be used, the RO water directly. This is my work. Yeah, this is the first time in my research group. Use RO water directly. Definitely we need to develop a new catalyst. Yeah, this blue line is the commercial system. You can see the pure water, DI water, and the very expensive catalyst. All the catalysts, the red line, all the catalysts, we use RO water directly. Okay, we can run 1,000 hours. This degradation rate is very, very low. Yeah, so compared with public results, our case is best. Okay, we also calculate the hydrogen cost. Here, we can meet the U.S. Department of Energy, the 2026, the cost target. Okay, we in my research group not only study the seawater, but also we study the fresh water only also. So for fresh water, actually there are big problem also. The first one is most of the study use iridium catalyst. This iridium catalyst, very, very expensive, very expensive. If we reduce amongst, the iridium, the, activity is low. So this reason a lot of people focus on that study. So in last 6 months, the 3 papers published in the Science. Yes, one paper is Japanese say, okay, we can reduce use amount of iridium. The second one is we can use iridium. Iridium price is much lower, but stability is not so good. So Chinese the college say, okay, we can less rhythm operates a very long time. Okay, he parked another science also. Okay, so you can see here, so very important, we need to consider, reduce use amount of rhythm. Second one is, so make rhythm catalyst very, very stable. The third one is, you can see, we must consider operate at a high current density. Why? Because efficiency is high. Yeah, currently is current density is lower than the 3, so not good enough. According to the DOE the target, you can see here we must the 3 is the target. Okay, in our system, you can see we use enomer, so the coating on the surface. In that case, we can make this catalyst run the long time. You can see, yeah, so modified, no modified. You use enomer on that. We can run catalyst 2,500 hours. Very important. You can see the current density. Our 6 much higher than DOC requirement. Yeah, this is you can see the degradation rate is very low. It's close to 0. So we also calculate the hydrogen cost is $2 for 1 kilogram hydrogen. Okay, so this published, but we submit to Nature Tactics, and so we return the revised manuscript already. Okay, in my research group, so we finished 100-watt system. So 1 kilowatt system finished already. This one is produce huge amounts of hydrogen. We cannot operate in the campus. Yeah, we must consider collaborate with industry, because a huge amount produced is not safe in the campus. Okay, so second, I would like to introduce a catalyst application in lithium sulfur battery. Okay, so for lithium sulfur battery, so why we study lithium sulfur battery? Because the energy density is high. It's higher than the the lithium ion battery. Yeah. So now for all the car, maybe we can after charge we can the driver the 400 500 kilometer. But if you use lithium sulfur battery, maybe we can drive the 1,000 kilometer. But currently, so this battery is not available for the commercialization, because its energy density is high, but power density is low. It means the discharge is very, very slow, and the most of capacity cannot use for during the charge discharge, because this kinetics is very, very low. So we must consider use catalyst for both kinetics. Okay, in this research, we use first we use a different catalysts, the metal catalysts that study the kinetics. Yeah, first we use Charter principle, establish a relation between kinetics is a reaction rate with the poly sulfur concentration. Yeah, after that we establish kinetics and material structure. Okay, after that we can get the equation. From that equation we found that for the polymer thin catalyst has the best performance. We can finish charge discharge in 5 minutes. Okay, this is very fast, right? So yeah, we you can see in our case, very high sulfur area loading and lean 11 products because this is commercial condition. Okay, so here you can see in the battery, actually there are different reactions. So yeah, at a different voltage. So here it's a different, the polysulfur products. Okay, this if we don't use a catalyst, this after use a catalyst, you can see the conversion rate the increase and the rate increase significantly. Okay, so this one is the quantitative only. So here you can see, yeah. So so before this study, nobody can measure the concentration of polysulfur in the battery. My students established a new system. Okay, use a UV system. He can measure the concentration. Okay, for example, here at 1.1 voltage. So yeah, for the this 320 nanometer, we can measure the single. So after that, we can measure concentration of lithium ion 2 and sulfur 4 concentration. Similar, you can see we can measure the different polysulfur concentration for different catalysts. After that, we can calculate conversion efficiency related with the polysulfur concentration. Yeah, this for the different reaction. Okay, it means if we want to achieve the higher dynamic current density, we must consider increased polysulfur concentration. Okay, yeah. After that, yeah, we use the same method. Yeah, so measure the concentration of the polysulfur at different the scan rate. Actually, this scan rate is indicate different charge rate also. You can see this is a linear relationship, right? So finally, we can establish this one, log G. J is current density. Log C is polysulfur concentration. Yes, this relationship is the scan rate is charge rate. Okay, so from this relationship, we can calculate the capacity of a battery. Okay, this one is predict with kinetic trait. It means from all equation. Okay, that one is experiment. It means we assemble the battery. After that, we can measure capacity here. This is capacity. Okay. This one is experiment. You can see two methods match each other very well. Okay. Now we establish a relationship between the kinetics and polysulfur concentration. But problem is we cannot measure the polysulfur concentration every time because we need to open the battery. If we must consider establish another relationship. It means you keep with a catalyst, you keep material. We can predict polysulfur concentration. In that case, we can establish kinetics and material property relationship, right? So here you can see we use this number is Eg the T2G. This one is the electron number. So we call the octopase of optical. This is a property of the material. Yes, and we establish this relationship with polysulfur. How we can get this number? First, we can use the DOS. This is the simulation calculation. Okay, you give material, we can get this number. It's this one. For iron, copper, the different catalysts, Yeah, this number we can calculate. Okay. This number can get from the experiment. This is a synchrotron result. From a synchrotron, we can measure this number. You can see for different cavities. Yeah, take a look. This is very close each other, right? Very close. So if we, plot to this dashed line, the EG over T2G. Yeah, you can see with the polysulfide concentration. So one is experiment, another one is calculation. So this match each other very well. This indicates in the future. Okay, you give material that can calculate. Okay, which one is best? Okay, so here you can see first this one we use this one the measure already. So we establish the equation. So after that we predict. Okay, for the covalent link material, this material has a high EG over 2 T2G number. This means the polysulfide concentration is high. Okay, so we use this catalyst. The battery. We study performance. This capacity. You can see this one. All the material, the predict material performance is much better, right? We also, after run the 100 hours, so we can, open the battery. We analyze, the material surface. You can see the very uniform, polysulfide color on the material. However, if we don't use all the catalysts, you can see different particles. Yeah, this is reason. So yeah. After we get the conclusion, so for the cobalt zinc catalyst is the best, right? So we use that catalyst several the battery. After that we use the measure the battery performance at a different rate. Okay, finally, you can see if we don't use any catalyst, you can see this red one, capacity is very low. This is not, so it means that this battery doesn't work very well. If you use all catalysts, you can see all the capacity is very high. Okay, we also study the battery performance at different conditions. But finally, we found that, at this condition, you can see we can run the 1000 the circle. So compared with the popular results, we can finish discharge in 5 minutes. Okay, it's very fast actually. Okay, so third topic is aqueous zinc iron battery. Okay, first, so we need to answer the question why we study this battery. Okay, maybe everybody knows. So for the lithium-ion battery, the big problem, one is explosion, another one is fire, right? So it's very dangerous actually sometimes. Yeah. So for some car, it's a fire or explosion. The second problem is very expensive. Lithium-ion battery is expensive. If we use aqua batteries, okay, we never, because we use the water as a solvent, so very cheap, and we don't have a risk of fire and explosion. Yeah, very important, charge rate is very fast. And so this process is very simple, because we don't need to, any protection. We can operate in the air and water, no problem. So, okay, so what is the application of aqueous zinc battery? Yeah, first one is smart grid, and second one is a household solar panel system. Because this, the volume, the size is a little bit large. Yeah, this kind of battery cannot use, the mobile phone and the car. But it's very good for the smart grid and household solar system. Okay, So why we studied zinc iron battery? You can see iron locate, HER and OER's window. This means, so we can make, the thermodynamic stability window is broad. Yeah, so we can avoid the OER. The second, zinc potential is low. Yeah, it means, work window of every battery is broad, so we can operate as a high output voltage. Okay, the big problem for this battery is shuttle effect. What means is the shuttle effect? It's the iron actually at this side is the cathode side. Pass the field, go to another side. In that case, make Coulomb efficiency is low. It means no high percentage of electrons work in the battery. The second one is serious self-discharge. This means we put the battery there, maybe 1 day or 2 days. The capacity lose a lot of. Second one is anode corrosion. So it means the battery lose function very quickly because the shortcut is okay. Here you can see we develop a new different method, prevent the shuttle effect. First one we use this one is imidazoline base as the additive. Yeah, we call this one is BMS. This BMS can suppress shuttle effect. Yeah, I will tell you why. Very important, you can see performance of the battery. You can see the higher activity mass loading. This means all the material energy density is higher compared with another study. Second one is a high zinc utilization. Okay, so most of the people, utilization is very low, the 10% or 20%. In that case, the energy density is low. In our case, it's very high. And the third one is low self-discharge. After 1 month, they lose 11% electricity only. For another people, 1 day, they lose most of the charge capacity. Okay, we can run the 5,000 circles. This is very long already, actually. Okay, why? If we use this, the additive, so you use this imidazoline, we can, prevent shuttle effect because this molecule has this structure. Okay, this structure is a nitrogen plus. He can, he can bonding, the poly iron. Okay, it's iron 3 minus and 5 minus. This reason, so that we don't want to give a detail. Okay, technical performance. If we don't use, the BMS, you can see this blue one is, the battery is a short circuit is very quickly. If we use this chemical molecule, you can see we can run a long time. Yeah, this discharge rate I just mentioned already. So we also study the performance as a different rate. So why we study the different rate? Because at a low different rate we can find the side reaction. Okay, if run very fast, we cannot find the disadvantage. Okay, finally you can see the very high DOD is zinc utilization is over 68%. So very high already. We can run 5,000 circles. How about another study? Yeah, you can see the highest performance is 500. Okay, so 5,000, 10 times. Okay, the DOD, high DOD is better, right? So our DOD is I just mentioned 68 already. only one publication is highest, but it can run only the 50 hours. Okay, we also compare self-discharge rate. This all catalyst, this all the battery. Okay, compare with the lithium battery and the lead acid battery. So this all is very low, right? Okay, so it's one method. Another method, we can use a dry method to produce electrodes. Okay, most of people use a wet method to produce electrodes. In that case, the area capacity is very low. It's low as 6. However, if you use all the catalysts, it's very high. It's close to 16, right? So you can see performance is very good also. Okay, you can see the after 750 circle, then we can keep capacity as 89%. Okay, this the video for this method. Yeah. Yeah. Okay, so you can see this method can be used for some large scale production. Very important, this method, the loading of atom is very high. It's 80. Another people may be lower than the 30. Okay. Okay. So now, we also in this battery, if we don't add anything in the the solvent is electrolyte, you can see this short circle is very fast, right? We must consider make battery longer, so run a long time. So this reason in this system we add this molecule. After we add this molecule, you can see we can run 5,000 hours, 4,000 hours. So yeah, what reason? After we add this TXE, we can measure the SCI film produced on the anode, the electrons. Okay, this reason we can so prevent anode. Okay, so you can see here we can use actually is FTIR. So the demonstrate observe this SCI film so produce on the surface. Okay, this performance. Okay, you can see after add this the chemical TXE, so performance is much better. So we this the concept performance. This post cell. A post cell performance a big different concept. Okay, so you can see here for the post cell, even for the post cell, we can run the 500 the circle, keep very high the capacity. Okay, so the third method, we need to consider increase energy density. We just mentioned compare with the lithium battery, all the battery energy density is a little bit low, right? We must consider increase energy density. Yeah, we just introduced two work, but that's a two work based on the 2 electron conversion. This means, yeah, iron minus to iron 0, this conversion. Okay, in that case, capacity is 211 only. Yeah, energy density is 260. However, if we achieve this conversion, this conversion is 4 electron conversion. This means from minus iron minus to iron plus. In that case, you can see this two platform. You can see here is a 4 electron conversion. You can see this capacity is double, right? This energy density is much higher than double. Okay, problem is very difficult to achieve this conversion. Okay, so in this public work in this year, actually we achieved this conversion already. Okay, we use this chemical. This chemical, you can see we call this chemical is HMTA. This MTA, first we can you know, the bonding with polysulfur. In that case, we can avoid shock effect for the, you know, the two electron conversion. Yeah, this molecule can, you know, the bonding with iron plus. Okay, we can suppress iron plus hydrolyze. So after that, you can see in our case, we can run the 1,000 circle. Okay, yeah, so we can keep very high capacity. Okay, we don't want to give detail about, you know, this performance. Yeah, this indicate how we can prevent, you know, shock effect during the two electron conversion. This one indicate how we can suppress the iron plus hydrolyze. Okay, this performance. Okay, first we measure, you know, the CV curve. From here we can see the 4 electron conversion happen already. Yeah, we also identify from Raman system. Yeah, this iron plus. Yeah, so you know, in all the case, iron plus is very stable. Okay, we also study performance in the palm cell. You can see here. Okay, so after we add, you know, HMTA molecule, performance improve very significantly. So here to the performance, if we don't add any, you know, the HMTA molecule, so, you know, shock pump is very quickly. So if use all the method, we can run the 5,000 circle. Okay, keep very high capacity. Okay, this post cell, you know, the performance. This post cell. So at different, you know, the link utilization is means high DOD. In that case, you can see we can run the 350 circle. So keep a very high capacity. Okay, summarize my talk today. So first we introduce the water and the seawater splitting for green hydrogen production. So in my research group, we try to combine this, you know, the study process. The second one, we study, you know, the catalyst application in the battery. Yeah, normally, so many people study the, you know, the battery, use for battery application. Third one, you know, I introduce aqueous battery. Aqueous battery is very useful. Actually, it's a very hot topic, you know, for the smart grid electricity storage. Okay, finally, I would like to thank my university and the ARC, you know, the government research council. We also thank, you know, the industry as a partner. Okay, thank you for your attention. So I'm happy to answer.
Thank you very much for your nice talk.
Thank you.
Very challenging. So I imagine that there are many questions.
Very nice presentation.
Thank you.
What do you think about the commercialization of lithium sulfur batteries? Because, you know, there's plenty of problems there.
Which process?
What?
Which one you mentioned?
Yeah, the lithium sulfur battery. Lithium sulfur. What do you think about commercialization?
Yeah, so, you know, the next one, so currently is no study, you know, for the real application. So I mentioned the big problem is, you know, the kinetics is very bad. Yeah, because, you know, during, you know, the polysulfur conversion, so some reaction is a solid and solid reaction. That's very difficult. Even we use, you know, the you use a catalyst, it's difficult, you know, to convert 100%. So, you know, this study is initial, you know, the study.
But so, you have also the shuttling effect too, and the anode problems in the lithium sulfur battery.
Yeah. So most of the problem is kinetics actually. So you know the theoretic capacity is very high, but you know actually we achieve maybe it's half only, maybe lower half. So in that case, compared with the lithium battery, so performance not so good. Yeah, theoretically it's very high, but very difficult to achieve. This is the reason. So currently, it's nobody results can the commercialization application. Yeah. Thank you.
Questions? Luis?
Great talk. Thank you. So regarding your use of the reverse osmosis for hydrogen electrolysis,
yeah.
You're using a model solution for that, and in that case, which is the key component, and which is the component that is more troublesome for the electrolyzer?
Oh, okay, so for the PAM system and for the AEM system, it's a different problem. Yeah, for the PAM system, the efficiency is very high. This is a reason why a lot of people, studied the PAM system. But PAM system, first problem is cost. Yeah, so now it's the cost for 1 kilogram of hydrogen is over $3 is quite high. So reason is the tank is very expensive. Second one, is stability is not so good. So it's for commercialization we need to run the maybe 10,000 hours, but currently most of study maybe only 1,000 or 2,000 like that. Yeah, for the AWE system, yeah, so the big problem is stability also. Yeah, so normally a lot of problem actually is some problem is fuel. So second is the electrodes. For example, for the nickel catalyst, is actually in industry currently is commercialized already, but a lot of problem. Yeah, we need to run the long time. So another problem is electricity. If electricity come from the power solar system or wind system, it's a sense electricity not unstable. So we must consider the shuttle and the start system. So in that case, activity of catalyst not so good, lose activity very quickly. So yeah, actually so currently the different study try to study not only the catalyst, but also the manufacturer's method, how we can connect catalyst on the electrodes. That's a big problem also. Yeah.
Great job, thank you.
Thank you.
I was interested in the first example you shown when you have the chromium oxide on the cobalt oxide catalyst.
Yeah.
Which is the structure of the materials? Is it a coating? Is it a composite?
Oh, it's actually it's mix each other. Now the coating. Yeah. So so no special method, actually. So yeah, but the function of two elements is different. I just mentioned for the chromium oxide, it's a very strong Lewis acid. Yeah, so it means it can bonding with OH minus produced during the water splitting. Yeah, during water splitting we produce OH minus, right? That's right. So for the strong Lewis acid can bond it on the surface. This reason on the several molecular distance on the surface. Yeah, so it's a very strong alkaline condition.
And what about because chromium 3 is known because it's relatively inert to substitution, for example. Are they fast? The addition of hydroxide, is it fast or is it slow?
What's it low or fast? Is
you say the Lewis, the acidic Lewis as the character of chromium, but what about the kinetics of this?
Kinetics. Okay, it's a good question, but Yeah, so I never measured, the rate of, but it's from performance, final performance is quite good. Yeah, so, yeah.
Very nice.
Thank you.
¿Alguna otra pregunta? Sí, Ernesto.
What is the cost of your reverse osmosis, and how does this cost affect the cost of hydrogen in the end?
With which cost?
The cost of the reverse osmosis, how many dollars per cubic meter?
Okay, so
that would define what is the cost of the final hydrogen.
yeah, actually, nobody use RO water directly. So my research is the first report. So actually, the RO water cost is very, very cheap. Yeah, it's very, very cheap. So some people, say, okay, so your work actually, it's just a waste of money because, yeah, it means you don't need to study, after silver spinning because the RO process is very cheap. Why? You don't use the RO water. So yeah, but I just mentioned, big problem is, the RO water not good enough for the PAM system. So PAM system is very sensitive to, the ion and the metal ion. So in that case, lose activity very quickly. So currently, the commercial products, we must use DI water. However, DI water very expensive. Yeah, so maybe in your laboratory, you have GC, right? GC, in the machine, the PAM system produce hydrogen, in the GC. Yeah, if in this system, you find it's a column. That column is ID water, the producer. If that's lose a function, so your GC, doesn't work. Okay, so yeah, so if consider the price, yeah, so not only the catalyst occupies maybe 70%. Yeah, we must consider another, for example, the fuel and a lot of different problem actually targeting. Okay.
Hello.
Okay.
I was also interested in the LDH reactors you showed.
LDH.
Yeah, these are metal electrodes modified by LDH,
Yeah.
made in situ.
Yeah.
Okay.
Yes.
And the role, I didn't understand very well the role of the phosphate. Is a proton shuttle or something like that?
Okay. Actually, this the phosphorus going to the double layer. The inside, the pore inside already. So you can see the double layer, the distance is changed already. So we have the plot, for the different ion, so this distance is different. Yeah. And the structure is
And then
different.
you find that the role of those phosphates is linked to, I don't know, proton transport or easier electron transport, which is.
Okay, so yeah, we didn't study that one, but we try to establish between the activity with different the ion the basicity is we never studied how fast the transfer in the pore. So yeah.
¿Alguna otra pregunta?
Okay, 1 hour. Okay.
So, thank you very much.
Thank you.
And then we are ready for the second one.
A little question. You try to use the same zinc ion system for raw batteries.